Hello and welcome back to FeedVAM discussions series. Today we are going to talk about a small issue which is coming in the expression of material tangent expression which we got in the linearization process. So as we know that in the Fives paper they have not considered the nonlinearity of 2D constitutive law. They've assumed it as linear and they've only considered the geometrical nonlinearity there. So we are going to talk about this material nonlinearity also. That means the expression of 2D constitutive law, the stress resultants when expressed in terms of the strain resultants, the corresponding stiffness matrix C is nonlinear. It is also a function of 2D strains. So then there will be two terms coming in the expression of final material tangent. So we will have delta R1 and delta R2, and correspondingly we will have an additional C dash term coming in, and the expression of that C dash we have given over here. So this is in terms of initial notation, because in the matrix form it is not possible to get this expression. So we'll now show how we have got this expression. So let us look at first the terminology which is involved here. First of all, A is representing the vector of 2D in plane strains. It is a 8 by 1 vector. First three are representing the membrane strains. Next three are corresponding to the bending strains, and the other two are out of plane shear strains. So it is a 8 by 1 vector of strains, and phi is representing the shell configuration. So in the shell configuration there are 5 parameters, or if it is a 6 degrees of freedom it could be 6 parameters, 3 corresponding to the phi map, small phi, this is capital phi here. So small phi representing the mid surface configuration, and T map, the two T1, capital T1, capital T2 vectors, or it could be small t1, small t2 and small t3 vectors. So that is represented as a shell configuration. It doesn't matter whether it is 5 or 6, the whole derivation remain the same. So we have, let's assume that here we have 5 degrees of freedom system. So phi is a 5 by 1 vector, and phi epsilon at any small epsilon configuration if we consider, so as we do in Taylor series expansion, so phi epsilon we are writing as phi naught plus epsilon delta phi, and correspondingly the strain would be A naught plus epsilon delta A. Now this expression of phi epsilon is such that at epsilon is equal to 0, phi epsilon gives you phi naught. Yes, this is true. And if we take the derivative of phi epsilon with respect to epsilon at epsilon is equal to 0, we get delta phi. So this is a valid approach of doing the linearization, and this is the basic assumption of doing how we are doing the what kind of linearization we are considering. So that is mentioned in the paper, and from the same expression we get the expression of delta r also. So this is the directional derivative of r. So dr by d epsilon at epsilon is equal to 0 is, by applying the chain rule, dr by d phi epsilon times d phi epsilon by d epsilon, and dr by d phi epsilon at epsilon is equal to 0 dotted with delta phi, because this term is delta phi and this whole thing is nothing but delta r. So now C is your stiffness matrix is a function of strains. So this we have to keep in mind. Now what we want to do is, in order to calculate delta r, we want to find dr by d epsilon. Means in the expression of r, which is this C of A times A, first we will substitute A in terms of epsilon. A epsilon is equal to A naught plus epsilon delta A, and then we take the derivative with respect to epsilon. So here is the expression of R when we substitute strains and both the shell configuration and the strains in terms of epsilon. Epsilon is a scalar parameter, by the way. Okay, just keep it in mind. Now if we take derivative of this r with respect to epsilon, we get these two terms from the product rule, one corresponding to this and another corresponding to this. So in the fee paper they have considered only this term, C of A naught plus epsilon delta A dot with B delta phi. They have not considered this term, so we are not considering this term also. So this term involves the derivative of the stiffness matrix with respect to epsilon. Now we substitute epsilon is equal to 0, so this term goes off, this term goes off, so this becomes B of phi naught and this becomes C of A naught, and then dC by d epsilon is now a function of A naught and delta I, because C is a function of A, so A we have substituted as A naught plus epsilon delta A becomes A epsilon. So dC by d epsilon now is function of A naught and delta A, and rest of things are as it is. Now what we want to do is we want to take out this delta A, which is right now in the inside the matrix. We want to take out this delta A because this delta is coming in all the terms, so this can be taken out, and this will get combined with the delta A which is coming over here, and then we'll get finally this form. So how we are going to do is, this is the expression which we got: delta R is equal to dC by d epsilon, where dC by d epsilon is a function of A naught and delta A dot with A naught plus this other term. These two are corresponding to delta R1 and delta R2. Now let us focus only on this term. So this term I am going to show you because this is in the matrix form, and in the matrix form it is not possible to take out delta A directly. So we will switch from here to the initial notation, and in this we are going to separate this delta A term. So let us see how we get this expression. Okay. So now let us consider that let us switch to the screen. Okay, now let's see, let's say we have C. Okay, C, it will be 8 by 8 matrix, and in all of these terms are a function of strains. Let's say this C11 term is equal to epsilon 11 square. Let's say it is like this, or maybe some other term is all terms are also there, epsilon 22 or something. It could be any expression. Now we substitute all these strains in terms of epsilon. So epsilon 11 will become epsilon 11 naught plus epsilon, which is the scalar parameters, times delta epsilon 11 whole square. Okay, plus epsilon 22 naught plus epsilon delta epsilon 22. Like that, this expression, this will be C11 epsilon. Now what we have to do is we have to take derivative dC11 epsilon by d epsilon, and this derivative we have to take for all the terms. Now this epsilon parameter is common because we have written all the strain terms in terms of a single epsilon parameter. Okay, so we have to just take the derivative with respect to epsilon. So we can write it like this, is equal to 2 times epsilon 11 naught plus epsilon delta epsilon 11, sorry, so there was a mistake, I have corrected this expression. So we just expand this square, so we get 3 terms here, and this has just 2 terms. So we have to take the derivative with respect to epsilon and substitute epsilon is equal to 0. So when we substitute epsilon is equal to 0, this term will go off because it is constant. This term will have a epsilon remaining, so this will go off, and only this term will remain. So we will get 2 epsilon 11 naught delta epsilon 11, and here we have plus delta epsilon 22. So this is the expression which we get from here. So you can see that it is a function of epsilon naught quantities, those are related to a naught quantities, and delta a quantities, delta epsilon 1 1. So you can write it as 0 times delta kappa 1 1 plus 0 like that. So basically it is a function of a naught and delta a, and all the terms will have these terms a naught and delta a, and we want to take out this delta a. So if we just look at this term which we got finally, this was the original expression of C11. So we can write it as dC11 by d epsilon 11, okay, and make epsilon 11, whatever we get out of here, make it epsilon 11 naught. That is the first thing which we did. And after that take its dot product with delta epsilon 11, and in all the terms the same thing is happening. In the second term we have this derivative coming out as 1, and we have delta epsilon to 2, and in other terms the derivative is 0. So this whole thing can be written as del Cij by del Aj, del Aq let us call it, because this is a different index. Cij is representing just any general term of this C matrix. So Aq times delta Aq, right? So this is the expression of this any general term of this matrix. So this is the expression which we got. Now if we look back in the PDF, so here we have written dc by d epsilon. So we have written a single term of dc by d epsilon in terms of I and j, and q is the summed parameter. So this is a general term of the matrix dc by d epsilon. Now this is dotted with some other term. dc by d epsilon is being dotted with a naught, you can see here. So that will take a different parameter, we are calling it as j over here. So if we have to take this dot with a naught, so we can write it as del Cij by del Aq dot delta Aq, and this, since it is dot product, we have to keep this j over here, so a naught j, okay, and then we just take this here and this over here, okay, because in initial notation we can transform the terms, we can switch the terms, their order doesn't matter. So we just write it as del Cij by del Aq Aj times delta Aq, and now this delta Aq is further broken down into Bqt delta phi t, okay. So we get the final expression as it is given over here, and this is the expression of Cij dash. So if we collect just this term, this becomes the expression of C dash, okay.